Hello everyone, this is Dr. Tasadduq Hussain, yet ready with another lecture on the inorganic chemistry. Today's lecture deals with the Max Planck's quantum theory of radiations, and this lecture will be divided into three different parts. So the first part will be discussing about the background. Secondly, we'll see what are the important postulates of Max Planck's quantum theory of radiations. And thirdly, we'll see what are the important achievements that Max Planck's quantum theory of radiations had. And it will be divided into two parts. First will be how it was able to explain the photoelectric effect and how it was able to explain the blackbody radiations. First of all, we'll go with the background. So this theory was put forward by Max Planck, the Max Planck's quantum theory. But before that, there came one more theory that's called as Clarke Maxwell's electromagnetic wave theory. This theory was put forward in 1856, the Maxwell's electromagnetic wave theory, and some of the important postulates of this theory were that the light travels as waves, though light travels in the form of waves which have a very small wavelength. And secondly, this Maxwell's electromagnetic theory also mentioned that the color of the light depends upon the wavelength. So the color of the light depends upon the wavelength or the lambda. And third important postulate was that the energy emitted or absorbed by a body is always continuous. So the body absorbs or emits energy continuously. It also mentioned that a black body emits a radiation of only one wavelength. So black body emits radiations of one wavelength. Only one wavelength of radiations are emitted by a black body. What is a black body? Black body is an ideal body which emits or absorbs all the frequencies of light. It emits or absorbs all frequencies of light. And it's called as a black body, and the radiations that are emitted by the black body are called as black body radiations. Another postulate of this theory was that the energy of radiation is proportional to the intensity of the radiation. So the energy of radiation is proportional to the intensity of the radiation. So the more the intensity, the more the intensity of radiation. So these are some of the important postulates of the Maxwell's electromagnetic theory, and this Maxwell's electromagnetic theory was unable to explain the black body radiations. It could not account for different things, and it was also unable to explain the photoelectric effect. The Maxwell's theory was unable to explain the black body, and it was unable to explain the photoelectric effect. And only after Maxwell put his theory of quantum radiation in 1901, only after that it was able to explain the black body radiations as well as the photoelectric effect. Now, if we see what a black body is, first of all, we should know what black body is. So if we keep an iron rod here, this is an iron rod, and I start heating this iron rod, so what will happen is this iron rod upon increase in temperature, so if the temperature is increasing in degrees Celsius, and usually the black body starts to emit the radiations when the temperature is going beyond 500 degrees Celsius. So at that point of time, what will happen is this iron rod is going to emit different kinds of radiations of different intensities. So initially this iron rod is going to be dull red upon increase in temperature, and then it will eventually turn into white when the temperature is again increased, and finally it will turn blue when the temperature goes to the maximum value. According to Maxwell's one of the postulates, a black body emits radiation of only one wavelength, okay, irrespective of the temperature. Now what we see in case of black body, we are increasing the temperature, but the radiations are not emitted of a single wavelength. The wavelengths are changing because the color is changing. As per Maxwell's theory, the color should not change. The intensity of only one color should increase. But in case of black body, what we see is as we increase the temperature, the color is changing. That means the intensity or the wavelengths of the radiations emitted are also changing. So Maxwell's theory was unable to explain why the black body emits radiations of different colors or different intensities. Now, in order to explain this black body radiation and as well as to explain the photoelectric effect, which I will explain in some of the later points in this lecture. So first of all, we'll go with the postulates of the Max Planck's theory of radiation. So we'll see how Max Planck's theory was able to explain this black body radiation as well as the what we call as the photoelectric effect. Now, Max Planck's theory, which was put in 1901, this theory was based on these many different postulates. So the first postulate was that the concept of quanta or quantum was given, or the concept of quanta was given by the Max Planck. So the emission or absorption of energy, light as well as any other form of the electromagnetic radiation by any body does not take place continuously. So the emission or absorption of energy does not happen continuously, rather it's happening discontinuously. How does that happen is that this discontinuous emission or absorption of energy takes place in a small packets of energy. So if we see, if this is a photon, so actually this photon is divided into smaller discrete packets of energies, and these small discrete packets of energies we call them as quanta. So this was the first postulate that was put forward by Max Planck, suggesting that the each packet of energy we call it as a quanta, and in case of light you can call this quanta as photon, because light contains photons in it. Now a photon is the smallest packet or smallest unit of energy or smallest unit of energy wave which can exist independently. So this small photon that I have shown here, or quanta, in case of energy we call it as quanta, or in case of light we call it as photon. This is the smallest packet of energy wave which can exist independently. So this quanta or photon, they can exist independently. So when you are seeing light, always it consists of a bunch of photons together. You are not seeing a single photon only. Now the second postulate of the Max Planck's quantum theory of radiation was associated with the energy. So he tried to calculate what is the energy that is associated with this small photon or quanta, and he calculated by using some of the principles of the physics and some of the principles of the classical concepts. He arrived at a conclusion that the energy that is associated with the photon or a quanta is always proportional to the frequency. So this nu here is frequency, is always proportional to the frequency of the radiation. Okay, and now when we remove this proportionality, what happens is this E becomes equal to h nu, and this h here becomes Max Planck's constant. We call it as Planck's constant. So this Max Planck's constant has a value which is equal to 6.626 into 10 raised power minus 34 joule second. Okay, and h nu is called as, it's also called as a quantum. This is actually the energy that is associated with the quanta. Similarly, the third postulate of Max Planck's quantum theory of radiation was that the energy, now since he calculated the energy, he also saw that this energy is always quantized, or it has fixed values. In other words, I can put it as the amount of energy that is emitted or absorbed by a body is a whole number, and it is a multiple of the quantum or multiple of the h nu. So in other words, E is equal to n h nu. Okay, so the n is the whole number, it's the multiple of a whole number. Okay, in other words, this means that the equation that I have shown here, we can show it as E is always equal to 1 h nu, it can be equal to 2 h nu, it can be equal to 3 h nu, but it's never equal to any fractional value. So this quantized energy, it's always a whole number. Okay, and it's never a fraction. So that means that the energy that is associated with the photon is always quantized, and this principle is called as the quantization of energy. These are the three important postulates that were put forward by Max Planck, and this equation can be simplified in other terms also, wherein we can say that E is equal to hc by lambda, because since nu is always equal to, the frequency of light is always equal to c by lambda. So in other words, this is also Max Planck's equation that we can use in our calculations. Now, since we discussed the background, we discussed the important postulates that Max Planck's theory put forward, and I also mentioned what were the reasons that this theory came into being, or the advantages that this theory have. The advantages or the achievements that this theory had will be discussed now. Already I have shown in the beginning that the achievements of the Max Planck's quantum theory were that it was able to explain the black body radiation, and secondly, it was able to explain the photoelectric effect also. Photoelectric effect. Okay, and these two were the limitations of the Clarke Maxwell's electromagnetic wave theory. So how did this Max Planck's theory explain the black body radiation? Was that according to Clarke Maxwell, the black body is supposed to the intensity of a single color should increase upon increasing the temperature. But what we see is that the intensity is different kinds of colors are obtained when we increase the temperature. So so the Max Planck basically explained this, that the energy is always quantized, and there are going to be, the energy is not emitted, the energy is not emitted or absorbed continuously, but it is discontinuous, and that discontinuity is because there are smaller photons or smaller quanta of energy that are there. Okay, so this clearly explained the black body radiations, and secondly, it was able to explain the photoelectric effect also. Now the photoelectric effect was basically initially given by Hertz in 1887, and it stated that the electrons that are ejected from the surface of a certain metal, so if this is a certain metal and it has electrons in it, and these electrons are ejected only when the surface of a metal is exposed to light of appropriate frequency. So if any light is falling on this metallic surface, this light has a particular frequency nu, and this particular frequency is only able to remove this electron. So this electron moves outside with some velocity. This phenomenon is actually called as the photoelectric effect, and according to the wave theory which was put forward by Maxwell, both the number of electrons ejected and their energy should be dependable upon the intensity of the incident light. But in practice, what we see is that the number of electrons that are ejected does not depend on the intensity of the light. So the number of electrons that are ejected, it does not depend on the intensity. So wave theory said that it depends upon the intensity, but it does not depend upon the intensity in practice. So to explain how the photoelectric effect was basically explained by Max Planck's quantum theory of radiation. So before moving further, it's also important to understand that what photoelectric effect constitutes. So I will not explain photoelectric effect here. I will just point you out towards one of the important postulates that is there, that will help us in understanding how Max Planck was able to explain the photoelectric effect. So the radiations that are that the metal is exposed to, they should have some threshold frequency, and only then they are going to eject this electron from the metallic surface. Okay, and any radiation that has a frequency smaller than this threshold frequency is never going to eject any electron, no matter how long or how high the intensity is. So it does not depend upon the intensity. Okay, and the magnitude of the threshold frequency is always different for different metals. So for different metals it's going to be different. So for example, if it is potassium, or if it is rubidium, for example, the threshold frequency is always going to be different. So this is one of the very important points that the photoelectric effect says us. Now we'll see how the photoelectric effect was explained by Max Planck's quantum theory of radiation. The major equations put forward for photoelectric effect were by Einstein in 1905, for which he got his Nobel Prize also. So the photoelectric effect was basically explained by Einstein with the help of the Planck's quantum theory of radiation. Now since already we know that according to Max Planck's theory, energy of a photon or energy is always equal to h nu, and it's always going to be conserved or quantized. And for photoelectric effect, we know that this frequency nu has always to be greater than the threshold frequency. Only then the photoelectric effect is going to happen. And now we know that the energy that is associated with the photon is equal to the product of Max Planck's constant and the frequency or the threshold frequency. We also know that the photoelectric effect will be in effect only when this threshold frequency is greater than the threshold frequency. When an electron is ejected from the metallic surface, so when an electron is ejected from the metallic surface like this, so in order to eject the electron from the metallic surface, the energy that the photon has, that is h nu, this energy is divided into two parts. One is the velocity or the kinetic energy that then electron gets, with which it is moving out of the metallic surface, and the second thing is the binding energy or the energy with which this electron is kept, in the metallic surface. We need some energy to take it out of the metallic surface, and then some of the energy with which the electron moves away from the metal. Okay, so in simpler terms we can say that the energy that the incident photon has, that is E is equal to h nu, this energy is always equal to sum of two different energies, and one energy among them is the kinetic energy, which is half of mv square, and then the rest of the energy is converted into, we call it as h nu naught. Okay, this energy is divided into two different parts I mentioned here. So half of the part is going to be the half of mv square, that is the kinetic energy, and half of it is going to be the h nu naught, and h nu naught is basically this threshold frequency. So nu has to be greater than nu naught, the threshold frequency. We sometimes also call it as the binding energy. This we also call as the binding energy with which an electron is held in the metallic surface, and the half of mv square is this. So we will represent this by half of mv square, and this binding energy here, this will be represented by h nu naught. Okay, so this now simplifying this equation, it simply becomes that the energy h nu is equal to half of mv square plus h nu naught. Okay, so in simpler terms we can also say that the energy that is associated with one of the photons of the incident light, which has a frequency nu, this is always going to be equal to the minimum energy that is associated with the photon, that is the threshold frequency v naught, to separate an electron from the metallic surface, plus the kinetic energy of one of the emitted electrons. I will just put this equation in more simpler terms so that it becomes more understanding. In simpler terms we can say that the kinetic energy, if I have to calculate the kinetic energy that is required, or the kinetic energy with which the electron is moving away from the metallic surface, that always becomes equal to the kinetic energy of electrons, and it's in joule per mole, okay, divided by the Avogadro number. Now the Avogadro number always comes into play in the chemistry. The equation that I have shown here, that is this equation. The equation here, I will label it as equation first. So this equation first was tested by Millikan, one of the physicists. So Millikan tried to determine the kinetic energy which corresponds to the incident light of frequency nu, and also the frequency nu naught, that is the threshold frequency. With the help of these kinetic energy values that he got from these equations, he calculated the value of h, that is Planck's constant, and his value came close to 6.570 into 10 raised power minus 34 joule second. And we also know that the Planck's constant has a value of 6.626 into 10 raised power minus 34 joule second. So the experimental value that the Millikan actually calculated is in a very close agreement with the Max Planck's constant. So this clearly indicates that the photoelectric effect was explained by the Max Planck's quantum theory of radiation. Also, it's important to understand that this equation. From this equation, you can calculate h nu, you can calculate the kinetic energy, you can calculate the binding energy with which an electron is bound with the metallic surface. So if I have to, for example, if I have to calculate the h nu naught, so it will be equal to h nu minus half of mv square. Simple. So you have to just transpose the terms, and this kinetic energy can be also calculated by half of mv square. I'll keep it here, and then h nu is there. This h nu naught will be transposed to the left hand side, so it will become h nu minus h nu naught. Okay, the threshold frequency and the original frequency of the incident light. So this also tells us that there is this is also in accordance with the law of conservation of energy. Okay, law of conservation of energy. Okay, so the energy is always conserved. You can see that the energies are conserved. The kinetic energy is equal to the two different types of energies, that is an intensity, the energy of the incident light, and then the binding energy. So in simpler terms, if I put it more simply, is that the energy of this incident light is divided into two different parts. So this h nu is basically divided into two different parts. One is half of mv square, that's the energy taken by the electron to have a certain sort of velocity, kinetic energy, and then rest of the energy is utilized in kind of taking the electron from the metallic surface, which we call as binding energy. So this is binding energy, and this is the kinetic energy part. So if you write it simply, you can say that the energy h nu, E is equal to h nu, is basically divided into two parts. One is half of mv square, and it's the velocity, it gives the electron in velocity, and the rest of the energy is converted, is basically utilized, that's h nu naught, and it's the binding energy. I think that pretty much concludes my lecture here, and I hope that you guys understood most of the stuff that I have shown here, and you liked the lecture. And if you did like the lecture, kindly subscribe to our channel. Thank you for watching.